I'm very excited today to show you how easy it is to start developing with Redis Tech. In this demo, I will showcase you the 3 pillars that build up to Redis Tech. I will show you the developer tools, Redis Insight. I will create the Redis Tech database on Redis Enterprise Cloud. And I will also show you how to use the object mapping libraries to build an application with Redis Tech. You can download Redis Tech today on redis.io. But you can also use your favorite package manager such as apt, yum or brew to install Redis Tech. In this demo, I will use brew to install Redis Tech. The first thing we have to do is we have to add a Redis Tech tab to brew. Now this is finalized, we only have to do brew install Redis-stack. This brew package, Redis Tech, installs 2 components. The first one is Redis Tech Server. Redis Tech Server is your favorite Redis extended with 5 modules. Redis Search, Redis JSON, Redis Graph, Redis Time Series, and Redis Blue. It also installs Redis Insight. We can now simply start Redis Insight by typing Redis Insight. Once we're in Redis Insight, we have to add a Redis database. I could use the Redis Tech server that was installed with Brew, but instead I will show you how to create the Redis Tech database in Redis Enterprise Cloud. The first thing I have to do is to log in or sign in into Redis Cloud. Then I can create a new subscription. You can create a free subscription for a 30 megabyte plan in any region that you wish. So we're going to choose EU West 1. We'll give it a name, Stack, and we'll go ahead and create the subscription. Once we have our subscription, we can create a new database. We can choose between a Redis Tech, a Redis, or a Memcache database. We'll also give this one a name. Now the endpoint is available. We'll go ahead and we'll copy this endpoint and add our database to Redis Insight. Add the Redis database. We paste the connection details here. And then lastly, we also have to copy the password of the default user. We can also go ahead and give this a new name. The database has been added successfully. We can see the 5 modules that build up to Redis Tech. Once we connect to the database, we will get into a browser. Redis Insight is designed to help you visualize data that resides within Redis and to help you build and optimize your application with Redis or Redis Tech. In the workbench, you can find different guides. There are guides for document, graph, time series, vector similarity search, and probabilistic data structures. There is also a Redis Tech tutorial that walks you through all the capabilities. There is a deep dive session later today that you can follow to see all the capabilities that are part of Redis Tech. Just to show you how it works, I will give you an example with the document guide. We'll click on Working with JSON. The first thing we'll do is we'll create some documents. These commands will create 4 schools. Now this is done, we can actually check in the browser what the content is of those keys. We'll go into school 1. We will see that the school has a name, a description, school type, etc. I want to continue my guide. I could continue with the CRUD operations, but I'll continue to create an index. I won't dive into the details, what is part of this index, but what you can see here is that, for example, the name is being indexed of the school. Now this index has been created, we can go ahead and we can search the documents. We can do, for example, an exact text search. Here we're doing ft.search schools, which is the name of the index, and I will search for girls. And there we go, we found 2 schools out of the 4 documents that contains girls. The last thing that I want to show you is how easy it is to get started building an application with the object mapping libraries that also build up Redis Tech. The only requirement that is part of my project is Redis Own. This is the object mapping library that is part of Redis Tech. I just have one file, I'm importing this object mapping library. The first thing that I will do is I will create a class that describes a person. There's a first name and a last name, and notice that we'll also index the last name. The next thing we'll do is we'll create a new person, Antires, who is, by the way, the creator of Redis. His first name is Salvatore and his last name is Sanfilippo. Then we'll go ahead and save Antires into our database. The next part is actually required to create the indices for Redis search. In the last step, we're going to show you that the object was saved by doing a full text search on the last name field. We're going to find the person that contains the last name, Sanfilippo, and we're going to return all the ones that match. So I'll go ahead, and there we go. We can find Salvatore back in our database. So just to summarize, in this demo, I installed Redis Stack using Brew. We created a database in Redis Enterprise Cloud, and we connected to it with Redis Insight. To get started, we followed an onboarding guide with Redis for Redis JSON, and afterwards we built an application using the object mapping library, part of Redis Stack. This concludes my demo. Thank you.
Today, I'm going to guide you through the different Redis Stack capabilities and show you how easy it is to develop services from very different domains using just a single product. My name is Elena Kolevska. I'm a software engineer turned educator in the last few years. I'm with the technical enablement team here at Redis, and our job is, basically to make sure all the technical people, and especially new hires, know our systems inside and out. I'm a huge Redis geek, which is probably to be expected, but one thing that's probably less obvious about me is that I love mountain biking. I've always loved biking in general, and for many years my bikes were even my main form of transportation. But a few years ago I somehow ended up in mountain biking, and I've been really super passionate about it since. Here's a photo of me and my bike, super muddy and exhausted, but really super happy. Why am I telling you all this? Well, I kind of translated this passion of mine to today's demo. So we're gonna go through a bike shop demo where we're gonna sell bikes. In our shops, apart from us selling bikes, our users will be able to create their accounts so they can discuss their bikes or their journeys or different trails in the forums. And they can also share ride statistics, and they can follow each other so they can get updates on each other's posts or rides. We also would like to be able to suggest some relevant information to our users. Ads, yes, but also information about what their peers or people they follow think about the bikes they're maybe considering to buy, and so on. As a business, we would also like to be able to analyze sales data, and so on and so on. Well, what constitutes a bike? Well, what can we use to describe a bike? There are many parts, of course, and in our demo, we're not going to go into all the technical details, but we're going to look at a little bit more simplified model. So we're just going to look at bike type. Is it a mountain bike? Is it a road bike, a commuter, e-bike, and so on? The model of the bike, so the name of the bike, the brand, price, which is kind of important, the description, weight, and maybe a few other characteristics. Without further ado, let's go ahead and set up Redis Stack. Okay, let's start by pulling the Redis Stack Docker image and running it as a container. Well, here we see that we are getting the Redis Stack image, version 101 at the moment. And this image exposes two ports, 6379, the standard Redis default port, and 8001 for Redis Insight, the GUI. We're going to run this for now, but I'll just like to point out that if you have these ports occupied by some other services or maybe some other Redis server on your development machine, you can simply rebind this to another port. Another thing I'd like to point out is that you are able, of course, to pass your own configuration file if that's needed. So that's done by binding configuration file. So .v, and then you path to the file. And you connect that to redis-tag.conf. Okay, this is how that would look. Since we have some more time while the image is downloading, I would also like to mention that you can pass configuration directives, and that would look, you can use just environment variables to do that. So E and then Redis args. And then you simply pass the configuration directive that you want to set. For example, max memory of some value, or required pass or so. Okay, you can also use environment variables to set up modules arguments. So that would look something like E, and then just copy paste this so I don't have to type and make noise. Okay, so it would look something like this. In this example, we are passing the retention policy argument to the Redis time series. Okay. Amazing. We have Redis stack running now. So let's go and open our browser and go to localhost 8001, which is the port where we mapped the Redis GUI, Redis Insight. Okay. And there we go. We read it by Redis Insight, straight away connected to our Redis stack database. No need for connection strings, for username, password, nothing. So Redis Insight was aware that we started the Redis stack and connected directly to the database. Okay, so let's move on to the workbench area here, where you can find different quick guides that can be really helpful for you to get started with Redis in general, and of course with Redis stack. And actually, let's let's focus mostly on the data modeling in our web shop. We're not going to write code. That's not what we're going to focus. I mean, we will show that in the end a little bit, but it's not what we're going to focus on in this tutorial. I would like to show more what you can do with your data model, how you can model your data, and what you can achieve with the capabilities that are offered here. So let's start with JSON. In Redis stack, you do have the option the possibility to work with JSON, which is not, as you probably know, is not a native Redis data structure. People have been using hashes maybe in the past to store JSON, but that's not really the most optimal way to do it. So let's see how does that look. If we by clicking these buttons, the commands and the queries that I pre-prepared are gonna just show up here in the work in the editor area. Okay, so if I want to create a bike that looks something like this here, I will simply run the command json.set. I will give the key name bikes1. I will give the $, which is indicating that I want this JSON string that I'm going to pass to be put like in the root, and I'm going to pass the JSON string that I want. As I mentioned before, we're going to model our bikes very, very simply, just a model, brand, price, type, description, and then we have specifications. That's actually a nested object, okay? And Redis stack handles this perfectly. So let's go ahead and run this. You can run it by clicking this button, or also just by command and enter. And okay, we get an okay response. In order to get specific fields now, you simply run JSON get, and then of course the key name, and then you use JSON path to just access whatever property you want from the JSON object. So Yes, indeed, Redis stack does support JSON path, which is also a great step forward, and it really makes work with JSON very easy. So if I run this, I will see that I can get a nested property very easily, specs material, and I can get here full carbon, or I can just get the model Hyperion. This is of course superior to using to storing JSON just in hashes, because you can get every little property from the object, only the one that you want. You don't need to pull the whole object out of memory and then deserialize it, and then take whatever you need and then serialize it and store it again. If you need to update it. Okay, we can very easily also update bikes. You simply run again JSON set, but this time you point exactly which property you want to update. And in this case, maybe let's just update the model to Hyperion 1, and there we go. Okay, so let's just load more bikes here. I'm gonna run this query and I'll let it run for a little while. We have around 100 bikes here, randomly generated, but they still make sense for our shop. And then I would like to show you how you can actually index and query your data, which is, again, something that doesn't come natively with Redis, but with Redis stack you do have the possibility to finally be able to get a better insight in your data. So first of all, let's create an index. The syntax for this is ft_create, and then you give a pass on the name of the index, and you specify that you want this index to index field, to index JSON data structures, specifically keys with this prefix, bikes : and then you specify the schema. So in our specific case, we want to maybe search on the model, brand, and based on the needs of the business and based on what we want, we're going to have to search in the future. We're going to choose which fields we want to index. We can work with full text indices, numeric, tag, geo indices, and we'll see one additional extra surprise in the next section. Okay, so for our bike here, we're going to choose, again, a simple schema. We're going to index the model and the brand as text. We want them to be sortable. The price is a numeric. The type is a tag. It's just easier and lighter to index it. We can also, of course, index nested fields and so on. Okay, so description as a full text again. And now let's see how do the searches work. The syntax for this is ft_search index bikes, so this is the name of the index, and then you specify the field you want to query on, and you specify the query string, e-bikes in this case. So let's run this. Sorry, we didn't actually create the index here, so let's just do that. And then if we query by type, we're gonna see that a bunch of bikes were just returned here. And of course, we only see e-bikes here. This looks like a lot of information, so maybe we want to just show a specific type of bikes. Maybe let's just list the type here. So in order to do that, we can say type as type. We need to specify, we just specify that we're going to pass 3 arguments, type as type, and then we run this, and we get just the type field. Okay, amazing. So the filtering works. We can also query by multiple fields. So in this query, we are querying by type and also by price. This is for users that, well, okay, I want to buy, I'm coming to your shop, I'm browsing the bikes, I want to buy an e-bike, and my price range is pretty wide actually, from 200 to 1,200 euros or dollars. And here in this example, of course, again, we return only a few fields. Let's run this, and we see that in this specific category of e-bikes, in this specific price range, we have these 2 bikes, Titan and Palace. We can add even more search parameters. So in addition to category and price, we can also add full text search. So in this specific query, maybe someone is looking for mountain bikes in this price range between $1,000 and $3,000, and because they're maybe like me, riding in mud in rainy weather, they also want to have mud guards. Let's run that and see that indeed we get a few bikes back. Okay. We can also do aggregate searches. So you can actually see how many bikes do you have per category. And in a specific price range for this specific query. Well, you run the query, you filter by the field that you want on, and then you can group by specific field, and you can run a reducer. And of course, you can sort. Let's see how that looks like. And we can see maybe if we are doing stock and we want to check how many bikes we have in each category, we see that we can run a query, aggregation query like this, and see that we have 13 mountain bikes, 11 kids bikes, and so on. Maybe we want to run a query where we want to see the average weight, per category, and this would look something like this. I can just press the up arrow, by the way, to see the latest query, and this would be FT aggregate. We don't need to apply a filter, we just want to run the aggregation across the whole index. So we group by type, we reduce, apply the average reducer, and then we sort on that field. And then we can get some information. We can see that the average weight maybe for commuter bikes is 13 kilos, road bikes 12. We can see that kids bikes are lighter. Mountain, some probably full carbon, really light bikes, and so on. Okay. Next, let's introduce vector similarity search. Vector similarity is this capability of comparing and finding similarity between unstructured data. Those could be images. So, for example, you can compare how much two images are similar to each other or dissimilar. Or maybe you could search between unstructured text and compare semantics. So to see, even though two different texts are not using the same words, maybe they still have the same meaning. One example of that would be maybe you're searching for pants, the color of the sky, and you get results for blue pants. Okay. Vector similarity search is currently not supported for JSON, only for hashes, but support for JSON is coming soon. Let's see how does this look. But before we continue, let's just say that the way vector similarity works is almost magical, but not quite. I mean, there are still some, everything's based on math and machine learning in here. Basically, how this would look like from your point of view as a user is you would have your, let's say, unstructured text. You would pass it on to a machine learning model, which would create then embeddings. So it would vectorize the data, create embeddings, and then you store those embeddings in Redis. When you want to compare some other query string, you also need to vectorize it, create an embedding, and then compare pass that embedding onto Redis. And Redis is going to find the top K matches that are closer to the vector that you just passed on. Okay, so Redis doesn't help you to vectorize the data itself, but it does help you to store it, index it, and query it. Query vectors. So let's see how does this look. Let's create a hash with embeddings. And here we see the bike. It has a model, brand, price, type, material description, and here is how the description embeddings would look like. This is obviously not meant to be read by humans, so we're not going to do that. We're just going to run the query. Okay, let's continue, add some more hashes, and here we're going to add around 100 bikes again. And once this is done, we're going to create the index in which we're going to specify how exactly do we want to index these vectors, and which algorithms to use, and so on. Okay, all the bikes are in, and now let's create our index. Let's see how this looks like. It's very similar to what we created previously for JSON, but now we see that we are working with hash fields. We specify which fields we want to index, and here in the description embeddings field, we say that this is a vector. We use which kind of indexing method, so flat. We specify which distance metric we want to use. We're going to be using the cosine similarity distance metric. Okay, let's run that. And then we can run a few queries to see the power of this vector similarity search. So I'm going to run this query that's asking, hey, give me results for comfortable commuter bike. Let's do that. And here we're going to see the first result is going to be an e-bike, which is easy. So it's a good city bike. So sorry, the query was comfortable city bike. So yeah, it is a good city bike that gets you everywhere, fast. And then in its description, we can take a look and see that it says that was a short-haul commuter, plenty of gear range, mudguards and a rack top, bike that helps redefine what can be done for this price. So all of these characteristics classify it as a comfortable city bike. Or then we see perfect commuting companion, anyone just looking to get the job done, and so on. If we step this up and we look for commuter bike for people over 60, we can see what kind of results we're getting here. So let's look at the description here, for example, of the first result that we are getting. It says, best e-bike for people who still feel young at heart. Some motor, okay. Easy for seniors to use, okay. So it got the meaning of this, and it gave this bike as a result when we were searching for a commuter bike for people over 60. Okay, fantastic rating for seniors, and so on. So this is pretty, I don't know about you, but I find this pretty amazing. Or another example, female-specific mountain bike. We can just get some bikes here. The sister company to Nord, Eva, first and only woman-dedicated bicycle brand, designed by women for women, and you see that our vector similarity search was able to detect this and suggest it as a female-specific mountain bike. Okay, if we want to go even further, and here we see that for women we have some mountain bikes, road bikes, mountain bikes. What if we want to tune this query? So we can actually add some more filters here. We can still search by price and search maybe for mountain bike specifically. Okay, so we're gonna tune the query here. First we do the filtering, and then we pass that on to the vector similarity search. Okay, here's how that looks. And here we only get mountain bikes in this price range. That's vector similarity search. I find it pretty amazing. It works also for images, not just text as unstructured data. Just go ahead and test it out. Next, let's look at how we can use Redis with time series. So in this specific example, we are going to be taking we want to track events that happen on a timeline, and these events are going to be sales. For sales, we're going to track the timestamp on one side, and on the other side, of course, the value of the sale. Okay, so let's create the time series here. Let's say that we have multiple shops, maybe some are physical, some here are online shops, and all of them are, let's say, described here in this 5 time series. We can label these shops, so we can say if they're in region East or West, for example. these are not compacted. I'll explain what this means in a moment. We have this duplicate policy here. This just specifies that if you have two events happening at exactly the same microsecond, so two sales maybe happening at exactly the same microsecond, both of them are going to get aggregated in the same event, and the aggregation function that we're going to apply is we're going to simply sum them up. Okay, so that's what's happening in these queries. Let's run those, and we have 5 time series created. If we have a very busy shop that has a lot of events, a lot of sales, you wouldn't want to group those sales by microsecond. That wouldn't maybe make a lot of sense. But what would make more sense is maybe group them by day. So let's just go ahead and create some rules to automatically compact our time series into a more compacted time series, downsampled, where our sales are grouped by day. Let's do that. We specify the rule here, and after this is done, the compaction is going to happen automatically. Okay, let's load then some data points here. We just simply say this is something just randomly generated data. We say, okay, we add to different shops for specific timestamps, and we add some sales. Let's run this. Okay, we have all the data points in. And now let's go ahead and run a simple query. The very simplest one would be maybe something like TS range by sales 1. This says, well, okay, from the time series bike sales 1, so bike sales for the first shop, from the beginning of the time series until the very end, give me all the results and then aggregate them by the hour. And this is going to give us something like this. Redis Insight is automatically show a nice graphical representation, and then here we can also choose to show the points. So these are our data points. We can see where exactly sales were made. Okay, so this is sales by the hour. If we want to do sales per day, we can simply use the value in microseconds for day. Okay, so that's going to look very similar. This is for a single shop. What if we want to get data from all the shop across maybe a single region? So let's do that. In this case, the syntax is ts.mrange, which implies that we're going to be querying across multiple time series. Again, the range is from the beginning to the end of the time series. We apply the sum aggregation again by day, and then we apply the filter in which we specify the labels of the time series we want to be included in this query. So in our specific case, we want to query the West region, and we want to point out that compacted, no. So we only want results from the original time series and not the compacted ones. If we run this, we're gonna have a nice, we're gonna get a nice result here. We see the different shops, so the 3 shops that are in the West region are showed by different color. Okay, then we can show maybe all sales per region. So for both regions, East and West, again, TSM range from the beginning to the end. And then we want to group by region and then reduce. So we're going to see how many sales we have done per region and compare them to each other. Okay, moving further. This query actually looks very familiar, and maybe the query doesn't look familiar, but it should remind us that in the beginning of this exercise we created that compaction rule that was doing exactly this. So it was compacting results by the day and saving them in a separate time series. So we could actually run a query on that time series and be a little bit more efficient. So we can simply now type compacted yes, use this label because that's how we label the compacted series, and adjust everything else. So regions are again east and west, we group by region, and then we sum. Okay, if we run this, we're gonna get the same query, but it should run more efficiently. Okay, and in the end, let's just point out that you can also filter by value. So you can say, well, okay, give me only the data points between these two values, and this would look something like this. And there we go. If we map the points here, you can see where the sales were, and here the sales, and their value was between 3 and 5,000. Okay, and that's how we can use time series for analytics. Next up, graph. In Redis Stack, you have the capability to work with graphs. Again, this is not a native Redis data structure, but it is offered with Redis Stack. So graphs are a little bit, it requires a change, shift in thinking of how you model your data, but it's actually not that complex because it really resembles the way we talk about data in real life. So what I would like to model here is we have bikes, and bikes can be sold to users. The way this works is through a transaction. So a user can make a transaction, and the transaction will contain a bike. So that's one thing we would like to model the relationship between different entities. And then we would also like to model that users follow each other, and maybe a few more things. So let's start one by one. First of all, let's create a bike node, and this is how that would look. Syntax is graph.query, and then this would be the name of the graph, and then we use a cipher, simple cipher query language. Okay, so we created the node. Node is an entity, bike, and we give it a few properties. If we know that we're gonna need to query on them, we can store them here. If no, we can just store them in the JSON or in the hash. So let's run this, and we see that a single node has been created. There it is. Let's load some more bike nodes here so we can have a more complete graph. Okay, let's also create some users, just a few. Again, we are creating a node, in this case a user node, which has the user label. The bike nodes had the bike label. This is how we will be able to distinguish them, and it's of course easier to query. Okay, so let's create the users. Now we have 5 users. Okay, let's now model the bike sales that I explained. As we said, so we have a bike and a user. We already created those nodes. Then we're gonna create a transaction. And then we're going to create a relationship that is going to connect the user, so u, this is the variable of for this user, and the transaction. Okay, so first we're going to say that the user made a transaction, and then a transaction contains, this is the relationship type, a bike. Let's run that. And then let's run a few more connections like this. So modeling bike sales here. Okay. So next, let's model the thing that we mentioned since the very beginning of this demo, that users will be able to follow each other and follow maybe their rights or their posts and so on. This looks something like this. So first we use a match query to find a user with a certain name. a bike with a certain name, and then we're going to create a connection of type reviewed, so a relationship, more precisely in graph terminology, relationship of the type reviewed between them. This relationship is also going to have its own properties. So because we maybe intend to be querying on how many stars were awarded to a bike in this review, we're going to save the stars, the number of stars as a property here to this relationship. And we're going to just point to the review ID that is maybe the full review ID. There's probably some text stored in maybe some string data structure somewhere else in some string key. So let's run that and a few other of the same type. Okay. And in the end, let's just model that users can follow each other. In here, we're going to match different users. So node of type user, so with the label of user, with the name of Andrea. So you can see here that we can search by name, by the name property of the node. And then we select another user with different name, and then we simply create follows relationships, relationship of type follows. And we create this for multiple users. So now that we have all our data in the graph, let's see what kind of information can we discover, what kind of input can we get out of this data. If there's a user currently browsing our shop and he or she is looking at a bike, it would be helpful if we can suggest to that user some interesting points about that bike. So for example, if they follow someone that has already bought that bike, that would be amazing. Or if someone they follow has already reviewed that bike, that would also probably be a very positive signal for buying. So let's just, but we cannot know in advance, right? What connection would we have there, and which, if we imagine that we're modeling this maybe with a relational database, we wouldn't really know which query to table, which table to query. So with graphs, this is a little bit easier. You can simply say, well, okay, can you please reveal for me what kind of connection do I have between these two nodes? And for this, you run a query that looks something like this. You say, well, okay, I have this user node here, and then I have this bike node here. Can you please give me the connections between them, anything between 1 and 5 degrees? 1 to 5 degrees. I don't know how many, maybe they're directly connected, maybe they're connected through something else. I don't know, but can you please research that for me? So if we run this query, we're gonna get something like this. Okay, this is how our graph looks like. So this is the user that's looking currently at the bike, and this is the bike. We can see here that the user actually follows someone, Noah, who has reviewed this bike. So we can, if we think that's a good review, that would be a positive signal, we can show that. And there's also Mario, also a user who has reviewed that bike. There's also this user here who has, so this would be Alicia, who has bought this bike actually. So that's good. We have 3 people that have some kind of connection with this bike. And you can see that in these 2 relationships, there's only 2 degrees of connection through a user, and here there's 3 degrees of connection. We can filter this even further. We can say, well, okay, show me all users who I follow who have reviewed this bike. So I'm Andrea. Can you please show me all users who I follow that have reviewed this bike? And that's gonna look something like this. And here, this is us, Andrea, this is the bike, and we see that Mario and Noah have reviewed this bike. But we can filter this even further by saying, okay, well, I mean, I actually want to see only the good reviews, maybe. So then we query even further. Query looks like this. We can add a where clause here, run this query, and then we get that only Noah has actually sent a review for this bike that has a star rating bigger than 3. Okay, hope this is helpful and can help you create better recommendation engines. To finalize, let's talk about Redis Bloom and just mention the other probabilistic data structures in general. In Redis stack, we provide Bloom filters, cuckoo filters, count-min sketch, and top K, all of them probabilistic data structures. If you're not familiar, probabilistic data structures are a way for you to run operations that you can usually run pretty well with regular data structures, but you're gonna sacrifice some accuracy in order to gain speed or memory. So time complexity, space complexity. And maybe losing some accuracy, it's not an option in some cases, but in many cases it's actually a very, very good and very efficient option. In the case of Bloom filters, you get a certain negative result. So a Bloom filter determines if an element is present in a set. Okay, so let's say a set of favorite colors, and I want to check if my favorite color green is in that set. I ask it, hey, is green in this set? The Bloom filter is going to respond yes or no. If it responds yes, that might be true, it might not be true. I can't trust it completely, but if it responds no, I can be sure that that result is indeed correct. And this actually works great for many use cases. For example, how we could use this for our shop, maybe when users are registering and they try to type in a username they want to use, we can just check in the Bloom filter if that name has already been used in our shop. So it's a much faster check than going to the main database or going to a hash for this, and this can be kept in much smaller memory space. So we check the memory the Bloom filter. If it says no, we are sure that that username is not has not been taken, and we can continue using them. If the Bloom filter responds yes, then in those cases, in that portion of cases, we can then proceed to checking the main database and seeing if that element is if that username specifically is indeed in our database. Okay. Another use case is the one I'm gonna check here, is we can actually keep a Bloom filter per user, and in that Bloom filter we can store all the products that the user has bought. Bikes are okay, bigger. Maybe you don't buy that many bikes per year or per multiple years to justify a Bloom filter just for it. But in this shop, maybe we sell pedals, maybe we sell energy food or wardrobe. So there's actually a bunch of other products that can be added to that Bloom filter. So why would we need this? Well, if our recommendation engine, whatever we use for recommendation, maybe gives us some set of products that it would like us to suggest to a user as an ad, we can actually get those products and compare them to the Bloom filter to see if that user has already bought that product. If the answer from the Bloom filter comes as yes, then maybe we can probably just skip that, even though there is a probability it's not true, the user has not bought the product. If the response comes as no, then we are sure that the user has not bought that product yet, and we can go ahead and show it. So let's see how a query would look like here. A Bloom filter would maybe have the username and ID, and then maybe bought products, or we can name it whatever fits best. and these would be some product IDs. So we can add multiple elements to the Bloom filter at once. And we're gonna get result of 1. And then the question would look like this. Has the user bought this product? Let's see. We're gonna ask 2 questions for product. This is product A, product B. For one of them, it's gonna say, well, okay, there is no, okay, so this product here doesn't exist, and we can be sure that this product ID doesn't exist in our Bloom filter, and that this product ID maybe exists, maybe it doesn't. Amazing. Let's move on now to showing how you can connect to Redis stack from the outside. In order to connect to Redis from the outside world, you're going to need some client libraries. Today we're going to show Redis Py, which is the Python library. It's easily installable through pip, and once you do that, let's look at how you can use it to connect to your Redis database. You simply import it, and then you instantiate a pool, specifying, of course, the host and the port. Here we're just using the default values. Then instantiate the connection based on that pool. Okay, just to check that all of this works, let's print out information about our index. So when we are working with the search capabilities, we use FT. And we, of course, specify the name of the index. So let's just run that real quick. And sure enough, we see information about our index. Let's, for now, let's comment this out and see how we can add the document. Well, first you specify your document, instantiate your document. Here we're using a dict that represents nicely our JSON file. And then on our connection, we go our JSON, and we specify the key name, and we pass on the dictionary. All of that is set on the root. So let's just run that. Great, that ran. If we now try to go and get this document, bikes 34 maybe, we see what happens. So we use JSON, get the key name, and then maybe we want to get this nested property here, specs material, and we use just JSON path to get that. So let's see. Sure enough, this prints out the desired result. A really quick example of how we can query. So if you want to run the following query after search, this is exactly what we saw in the guide before. We can again run FT, we specify the bike index, and we run the search query. Type is new type. Let's save this. And there we go. We do get the result here, result document. Amazing. In the end, let me introduce to you Redis. If you like to do your modeling inside the programming language with the data structures that you already know and love, and not having to worry about how you're going to serialize the data, how you're going to get it from your programming language into Redis, then you might like the Redis libraries. ORM stands for Object Mapper, and it provides high-level abstractions, making it very easy to model your data. And it provides validation, provides serialization, and also persistence. So it abstracts the data model away from you. Sorry, the data layer away from you. Okay, in this example, we're going to show how you model a bike, a simplified version. So you would create it, basically you create a class, a bike class, and you specify what types of fields you have, and you define them. You define their types. You can mark them as optional. You can mark if they need to be indexed or not. And then when you want to create a bike, you simply instantiate that object with the fields that it needs. Let's run this what we have so far, and see what happens. Okay, there we go. So here we see the dictionary was created, model, brand, price, and so on. And the interesting part here is that the primary key was also created. Okay, so Redis home libraries use a fluent interface. We can simply run mybyte, then save, and actually keep chaining on methods. So let's see what this would do. If you simply run the save method here on this object, this is gonna do the serialization and the persisting to Redis. You don't have to know the Redis commands. You don't have to know how to serialize your object. You leave all of that to the library. Okay, that's done. So if you want to now get that key out, you simply look it up by the primary key. So bike, get, and then you pass on the primary key. Let's see how that looks like. I'm gonna comment this out in the meantime so it doesn't clutter our view. And there it goes. There we go. We got the byte back. And there we have it. I hope you liked and enjoyed what you saw as much as I do. We covered a lot today, so if you feel like you might gonna have to check some of the things again, don't worry. The tutorial is already available in Redis Insight. So just download it and have fun exploring Redis Stack. Until next time, take care.